Hello, welcome. In this part of the lecture, we will discuss curvature. Curvature of a curve at a given point measures how quickly the curve changes its direction at that point. Let's begin our discussion with the smooth curve. A parameterization is called smooth on an interval I if the vector function has the first derivative whose component functions are continuous and the derivative of the vector function r is not the zero vector on that interval I. A curve is called smooth if it has a smooth parameterization. A smooth curve has no sharp corners, like this, or like this. A smooth curve has also no cusps, like this. When the tangent vector turns, it does so continuously, as shown in the following figure. If C is a smooth curve defined by the vector function r, recall that the unit tangent vector, denoted by t, is given by this equation, 5.2.1. As said before, the curvature of the curve C at a given point is a measure of how quickly the curve changes direction at that point. Specifically, we define it to be the magnitude of the rate of change of the unit tangent vector with respect to the arc length parameter. We use arc length so that the curvature will be independent of the parameterization. Because the unit tangent vector has constant length, namely 1, only changes in direction contribute to the rate of change of the tangent vector. Let's have a look at a mathematical definition of a curvature of a curve. The curvature of a curve is denoted by the Greek letter kappa, which is defined to be equal to the magnitude of the vector, which is the derivative of the unit tangent vector with respect to the arc length parameter. The curvature is easier to compute if it is expressed in terms of the parameter t instead of the arc length parameter. So we can use the chain rule of differentiation to write the derivative of the unit tangent vector with respect to the parameter t equals the derivative of the unit tangent vector with respect to the arc length parameter times the derivative of the arc length parameter with respect to the parameter t. This is obtained by applying the chain rule of differentiation. Therefore, the quantity here is equal to dt over dt by ds dt. We just divided the equation by ds dt. Recall that ds dt In other words, S prime of t is by definition equal to the magnitude of the vector r prime. Since in the case of smooth curve, r prime of t is never equal to the zero vector, so this vector is a non-zero vector, so the magnitude of the vector is not a scalar 0. So we are safe to divide by the quantity ds dt. Now dt over dt is simply the t prime at t, and ds dt is equal to the magnitude of the vector r prime, as written here. But in the previous page, we defined the curvature kappa was equal to the magnitude of the vector dt over ds. Therefore, the magnitude of this vector ds dt here is the kappa, and we calculate the magnitude of the right hand side also, which gives the magnitude of this vector, which is 1 over the absolute value of the magnitude of r prime times the magnitude of t prime. Since this quantity here is a strictly positive quantity, so its absolute value is simply the magnitude of r prime. So we get the expression for the curvature as written in equation 5.2.2. Now let's have a look at an example. Show that the curvature of a circle of radius a is 1 over a. Let's have a look at the proof. The equation of a circle of radius a in plane can be described by the following vector function. R of t equals a cosine of t, I plus a sine of t, j. Remember, this is the x coordinate and this is the y coordinate of the point on a circle centered at the origin and radius a. Now this vector function gives r prime equals negative a sine of t, which is the derivative of x with respect to t, I plus a cosine of t, j. And its magnitude is the positive square root of the sum of the squares of the components, which is equal to the non-negative square root of the quantity a squared, which is the absolute value of a, but since a is positive, it reduces to a only. So the magnitude of the vector r prime equals a. Therefore, the unit tangent vector is given by this expression. In the numerator, we have r prime of t, and in the denominator, we have the magnitude of r prime of t, which reduces to a vector negative sine of t I plus cosine of t j, obtained by cancelling the a's from the numerator and the denominator. And the derivative of the unit tangent vector has components negative cosine of t and negative sine of t, obtained from differentiating the components of the unit tangent vector. So the magnitude of t prime equals the positive square root of the sum of the squares of its components, which simplifies to 1. Therefore, the curvature of the circle of radius a at any point is 1 over a. The result of the previous example shows that small circles have large curvature and large circles have small curvature, because the curvature is given by 1 over a for a circle of radius a. So larger the a, smaller the kappa value, or conversely, smaller the a value, larger the kappa value, curvature value, which is in accordance with our intuition. Because small circle has greater curvature, on the other hand, the larger circle has less curvature compared to the figure. It looks flat, but it is curved here. And we can also see directly from the definition of curvature that the curvature of a straight line is always 0, because the tangent vector is constant. The tangent vector at any point is not changing the direction. Theorem. The curvature of a curve given by a vector function r can be calculated by using this formula. In the numerator, we have the magnitude of the cross product of the vectors r prime and r double prime, which is the second derivative of the vector function r. And in the denominator, we have the cube of the magnitude of the vector r prime. Let's have a look at the proof of this theorem. From the equation 5.1.4, we have the magnitude of the vector r prime equals s prime. And the unit tangent vector can be written as shown in equation 2. Recall that the unit tangent vector was defined as so if we transpose this s prime to the left hand side, the equation will become as shown in equation 2. Now, differentiating the equation 2 with respect to t, we obtain this equation. So in the left-hand side, we obtain r double prime, the second derivative of the vector function r. In the right-hand side, we applied the product rule of the vector with a scalar function. Recall that if f is a scalar valued function and u is a vector valued function, then its derivative is given by the product rule we proved earlier in some section. So we have the equation 3. The cross product of the vector in the left-hand side of equation 3 with r prime gives this equation. So we take the cross product of equation 3 with the vector r prime. Now we substitute the vector r prime from equation 2 as s prime times the unit tangent vector t. This term stays the same. Similarly, the r prime here would be replaced by s prime times t. And the term here stays the same. Now, the first vector here stays exactly same, but the second vector here becomes the zero vector, because the cross product of a vector with itself equals the zero vector. Here, s prime and s double prime are the scalar valued functions. Therefore, r prime cross r double prime equals to the square of s prime of t times the cross product of the vector t with t prime. Since the vector t prime is orthogonal to t, as the magnitude of the unit tangent vector is constant, it follows from that t dot t equals 1. Now if we differentiate both sides, in the left hand side we obtain t prime t plus t dot t prime equal 0. Or, since dot product commutes, in the left hand side we have 2 t prime dot t equals the zero vector. Or by cancelling 2 from the left hand side, we get the dot product of t prime with t is 0. So t must be perpendicular to the vector t prime. Therefore, we have the magnitude of the vector in the left-hand side in the previous equation is the magnitude of the vector in the right-hand side. But the magnitude of a cross product of two vectors is equal to the product of their magnitudes times the sine of the angle between them. We call that the cross product of AB, and its magnitude is the product of their magnitudes times sine of angle between them. But the vector t has magnitude 1, since it is the unit tangent vector, as shown here. And theta, which is the angle between the vectors, is pi over 2 radians, or 90 degrees, since the vectors are orthogonal. So we have left with the magnitude of t prime only, which is written here. And then we have the magnitude of the r prime cross r double prime from the left hand side is equal to this quantity here. So this is obtained just by applying here the definition of the kappa, the curvature, which is the magnitude of t prime over s prime. So the magnitude of t prime is k kappa times s prime. So we have one more factor of s prime, and we have a kappa. Now if we solve the equation for kappa, we get the required expression as shown below. Let's have a look at an example. Find the curvature of the twisted cubic whose vector function has the component functions t, t squared, and t cubed at a general point and at the origin. Let's see the solution of this example. To calculate the curvature, we need several quantities. So we need r prime, r double prime, and these vectors, and the magnitude. So we first compute these required quantities. As we see, the vector r has components t, t squared, t cubed. So its first derivative has components 1, 2t, and 3t squared, obtained by differentiating the vector function of the twisted cubic. Similarly, if we differentiate this vector function again, we get the component functions 0, 2, and 60. The magnitude of the vector r prime is the positive square root of the sum of the squares of the components, which is this expression. Now we calculate the cross product of the vectors r prime with r double prime, which becomes this vector 6t squared I minus 60j plus 2k. So we have the magnitude of this cross product is this scalar function. Therefore, the formula of the curvature at any general point becomes this. And if we substitute t-value equals to 0, since t-value equals to 0 corresponds to the point 0, 0, 0, we obtained the curvature of the twisted cubic at the origin, which simply gives 2. For a special case of a plane curve with the equation y equals f of x, we choose x as the parameter, and then we can write the vector function of this plane curve as r of x equals xi plus yj, but instead of y we can use f of x j. So this vector function entirely depends on the parameter x. Now it follows that its derivative with respect to x becomes I plus f prime of x j. So if we differentiate x, we get 1. If we differentiate f, we get f prime. Similarly, the second derivative of the vector function r becomes f double prime of x j. Now if we calculate the cross product of the vectors r prime with r double prime, we get this vector f double prime of x times the k. So the formula of the curvature becomes this expression. So this is the formula for calculating the curvature at a point x to a plane curve given by the equation y equals f of x. Let's see an example. Find the curvature of the parabola defined by the equation y equals x squared at the origin 0, 0 and at some point 1, 1 on that parabola. Let's see the solution. Here f of x equals x squared, so f prime of x equals 2x and f double prime of x equals 2. Therefore, the formula for the curvature for a plane curve we just proved simply becomes this expression: 2 over the cube of the square root of the quantity 1 plus 4x squared. Now the points 0, 0 and 1, 1 correspond to the parameter value x equals 0 and x equals 1 respectively. Therefore, the curvatures at those points are given by these numbers. So the kappa at 0, if we substitute x equals 0, we get 2. And if we substitute x equals 1 into the formula, we get kappa at 1, which is 2 over the cube of the square root of 5, which is approximately 0.18. So the curvature of the parabola at the origin is much higher than the curvature of the parabola at the point with x coordinate 1. We also observe that the curvature function here has the property that the limit of the curvature as x approaches plus infinity is 0. And also, since it is an even function, namely the graph of the kappa would be symmetric with respect to the y-axis, it follows that the limit of the kappa function or the curvature function as x approaches negative infinity is also equal to 0. This corresponds to the fact that the parabola becomes flatter as x approaches either plus infinity or the negative infinity. As shown in the figure, the parabola is plotted with the green color and the curvature function kappa is plotted with the red color. So we see the curvature has the maximum value at the origin, and as x approaches infinity, the curvature function becomes flatter and flatter, asymptotically approaching the x-axis. Since the higher we go along the parabola, the curve becomes flatter. The circle shown in this figure is called an oscillating circle, also known as the kissing circle. It touches the parabola at the point A, and at that point the parabola and the circle both have the same tangent line and the same curvature. Please see the notes for the details.